Okay, in this video, I'm just going to be spending a few minutes talking about a review of digital logic that will be helpful if you are looking into embedded systems and trying to be prepared to understand all the content that would go along with embedded systems. So I'm going to start by talking about logic. When we think about logic, we think about things as either being true or false. And in the way that we conceptualize this for electrical and computer engineering, we think about logic as having either a 1 or a 0 value, where 1 is true and 0 is representing false. When we think about it like this, that's what is called positive logic. And if we have the opposite of that, then we have negative logic. So negative logic is the opposite, where 0 is true and 1 is false. In actuality, if I'm working with an embedded system, these logic levels are set based on the voltages for that embedded system. So in many embedded systems, that's either 5 volts or 3.3 volts. For the sake of this video, I'm going to talk about 3.3 volts, which I'll often abbreviate as 3V3. And 3V3 is corresponding to a logic 1, and 0 volts is corresponding to a logic 0. So if something is at 3.3 volts, it's true, and if something is at 0 volts, it's false. However, that's not actually exactly how it works, because in reality, I've got these bands of truth or false values. So I would consider anything from, let's say, about 2.15 volts to 3.3 volts to be true, and anything that's sort of below 1.16 volts to be false, and anything in between we don't really know. It's not allowed. So we try to make sure that that gives us a filter of whether something's true or false for digital values. One of the ways that we can implement digital logic is through the use of transistors. And in particular, we'll use what are called CMOS networks, or complementary MOSFET logic networks. And in order to make this work, you need to think of a transistor as a switch. So for an N-type transistor, and I'm working with MOSFETs here, where I have a gate, a drain, and a source. If the transistor is active, meaning that there is a voltage between the gate and the source that is sufficient to turn it on, it effectively looks like a switch closing or a short circuit. For a P-type, what I see, and I'll do my best to draw the representation of this correctly and quickly, what I see is here my gate is there, but my source and drain are flipped. And if I have a voltage on A that sort of would be activating an N-type, what it does is the opposite for a P-type. So putting a voltage there looks like a switch opening, and so it looks like an open circuit. And so when I connect these things together in one network, I get a complementary operation. That's why it's called a complementary MOSFET representation. So we'll look at a very simple network here that goes along with that. So let's say this is A. At the top, I'm going to have a PMOS. Remember, this is going to be source, drain, and gate. And I'm going to connect at the top my logic level 3v3, or a level of 1. Then down here, I'll have my NMOS, where this is the drain and the source. And right here between these drains, that's where I'm going to take my output. I'll call it Y. And Y, it turns out, is going to be equal to not A, or sometimes you'll see it written as tilde A, which means not A. So it's the opposite of A. What do I mean by that? Well, let's work out the logic in terms of like a truth table. So for different values of A, we'll say 0 and 1 or 3v3. And what happens with each of these transistors. So a p-type, an n-type, and then let's just say Y is here. Okay, so when A is equal to 0, what happens is that this switch here looks open. That's my n-type, so I would say that it's off. Instead of having a value of voltage there. So when the p-type is active, that means like the input for it is 0. That's where the switch looks closed. And so I've essentially got a wire connecting my output up to the 3v3, which means that the output Y is equal to 3v3. The opposite happens in the case when A has a voltage associated with it. So now the p-type looks like it's off or open, and the n-type looks like it's active or closed, and I get an output of 0 because I have a wire essentially, right? So instead of that being open, now it's closed. Can't spell, but it's closed, and so I've got a wire, whereas this is open, so it pulls that output down to 0. And what I would call this representation is an inverter. And the circuit diagram for that is here. We'll talk about the logic of it later on. Y is equal to not A. So continuing to talk about different types of logic representations, we should really talk about logic gates that happen in digital logic. And part of the reason we do that is in coding an embedded system, we're going to need to make some logical decisions based on whether or not things are true or false. We're going to do all kinds of things like that. So we're going to start with an AND gate. In C++, an AND is represented using two and percents. In writing, I represent it using like a multiply or a dot between them. And the gate looks like this in terms of our circuit representation for them. So let's just look at the logic of how AND works. Again, this should hopefully be review if you've taken a digital logic course before, but if this is your first time, it doesn't hurt to think about it. So what does A and B mean? Let's start by defining all the possible states of A and B. So A can be 0, B is 0, A can be 0 while B is 1, A can be 1 while B is 0, or they can both be 1. Y is only going to be true if A is true and B is true. So the only time I should get an output of 1 is when both of them are 1. And everywhere else, the logical value, the true or false value of that AND is equal to 0. Similarly, we can look at OR. In C++, the way that OR is represented is using two vertical lines. You can find those on your keyboard by typing Shift, and then it's the button right above your Enter or Return key. The way I write OR in writing is using a plus sign. So this reads Y is equal to A or B, and you can see the circuit representation here. Again, let's build a quick logic or truth table for this. Again, all possible values of A and B. And the way that OR works is that Y will be true if A is true or B is true. And so what that means is that anywhere that there is a 1 in either A or B, I get a 1 at the output. Building these up using CMOS is somewhat complicated, and I would push you towards another video, which I've linked in the description, where I talk about CMOS in more depth. Again, let's go back to the inverter. The logic table for this is fairly simple. So A is either 0 or 1, and Y is simply the opposite. Note that in writing, I usually put a bar over my A to represent not. In C++, you use an exclamation point to represent not. One more that I want to talk about is an exclusive OR, which essentially is telling you it is true, the output Y is going to be true if A is true and B is not true, or if B is true and A is not true. So when A and B are both true, an exclusive OR is going to return false because I exclusively am looking at one of them being true. And the circuit diagram is the same as an OR, except I add one extra line here. I'm filling in a little bit more darkly so you can see it. And I represent that in writing using a plus sign with a circle around it. So what does the logic for this look like? Well, first of all, just so you know, I've represented the logic, as I said, verbally. But the way that I would build the logic table for this is I would start by writing A and B. So again, all possible values of A, 0, 0, 1, 1, and B, 0, 1, 0, 1. So as I construct this, I might go ahead and write not A and not B. So not A is 1 everywhere that A is equal to 0, and 0 everywhere that A is equal to 1. And I'll do the opposite thing here for B. So now I can write out what is A and not B. Well, A and not B is true only when both are 1. So that looks like 0, 0, 1, 0. Similarly, what is not A and B? Not A and B, the only place where they are both 1 is right there, so I should get 0, 1, 0, 0. And so if I write this out as A and not B, or A and B, it would be true when either one of those is true. So you'll notice the top one's definitely 0, bottom one's definitely 0, and then I've got 1 in the other positions. And that's equal to that exclusive OR, A exclusive OR B. That's something, again, that's going to show up in terms of executing logic within systems. There is way more we could talk about. We could talk about not and or not or, which are actually practically much easier to implement using CMOS. But we're going to go ahead and stop at this point because this is what I think is most essential for a student to know if they are preparing for an embedded systems course.